So let us look at the torsional deformation equation of a straight wing, which we wrote it as dy plus q e c cl alpha theta equals minus q e c cl alpha alpha r minus q c square cm ac plus n mg. With the boundary conditions, theta at 0, that is the root, it is 0, and since there is no moment, it will be d theta over dy at L is 0. Okay. These are the boundary conditions. This is, we have used strip theory. That means every section of the wing is treated as a 2D aerofoil. We applied the aerodynamic moment and we just wrote the torsional deformation equation. Now, alpha r is the initial rigid angle of attack, you may call it, but this can be a function of y, that is along the span, and m can be a function of span, all these things. Now our aim is to establish what is the deformation of this wing and under what condition that the deformation will become very large. So for that, we look at the, first we take a very simple case of uniform wing. Then if my wing is not uniform, that means my Gj can be a function of the span, y axis, all these things, E, chord, everything can be a function of y. Then how do we solve for that type of situation? Okay, that is by approximate method. First let us say it is a uniform wing. When that means Gj, E, Cl alpha, they are all constants. Okay, and I look at the only the homogeneous part of the differential equation. That is not the particular solution, because I want to see how the homogeneous solution changes. What is the form of the solution and what condition it will meet to get your divergence field, because the key parameter is the Q, which is the dynamic pressure, which is half rho u square, which can vary with forward speed. Now if it is a uniform wing, you will have Gj d square theta by d y square plus Q E C equals 0. This is the homogeneous part, and this will be like a second order equation. You will have d square theta over d y square. I am putting it as some lambda square theta equals 0, where lambda square I call it as QEC CL alpha over Gj. Okay. Now this is the like a simple second order differential equation. The solution of this, you can write it as theta of y as a sine lambda y plus b cosine lambda y. Okay. Now you have to get these constants a and b from the boundary condition. Boundary condition is theta 0 is 0, which means this implies when you put y is 0, this term is 0, this is 1, therefore this says b should be 0. Then you put the second condition, that is d theta over dy at L. This is 0. This implies you will have, when I differentiate, this is going to become a lambda cosine lambda L. So you will have a lambda cosine lambda L. And if you say my lambda is not 0, a is not 0, I should have the condition cosine lambda L is 0, which means my lambda L is 2n plus 1 by 2. N can go from 0, 1, etc. into pi. Okay. Is it okay? Now this is the condition for your pi by, yeah. This is the, now what does it mean is, if lambda L takes the value, let us say for the lowest value is pi over 2. If it takes this value, then your solution is theta y equals a sine, because lambda is pi by 2 L y, right? Now a can take any value, because this condition essentially says I have satisfied my boundary condition and I have satisfied my differential equation. Okay, which is an exact solution. The condition for it to be satisfied is this, and you call this lambda L equal to pi over 2. This is actually the lowest value. That becomes your critical speed, which you call it as, I erase this part, your lambda square is this. So lambda critical will become pi over 2L. That is the first value. And you know lambda. So if you take lambda square, you will get that Q E C CL alpha over Gj equals whole square, because lambda square is pi over 2. You can find out this is my Q divergence, you call it, because that is my dynamic pressure at the divergent speed, for which I satisfy my equation, I satisfy my boundary condition. Now if we write our solution, now you say Qd becomes pi over 2L whole square Gj over E C CL alpha. Okay. Now you can find out what is the divergent speed. Divergent speed becomes, because Q is half rho ud square, you will put ud becomes square root of Gj over E C CL alpha into rho over 2 density and then pi over theta. So this is my divergent speed. Okay. Because you find this solution theta y equals a, whatever value of a you choose, it satisfies your differential equation. That is a homogeneous. That means basically you say this is like a buckling problem of a column buckling. Exactly the lowest value. That is why you say the lowest, the first value, you take it as the divergence speed. At that speed, any A is a solution. That means any amplitude, that means any of the twist value of the wing. But you cannot find out what is that value because it exactly satisfies that equation. Okay. And this is your for a uniform wing divergence speed. Now, if you look back your notes, in the sense, if you look at your for the 2D aerofoil, we wrote the divergence speed as, okay, let this equation be there, because we had the 2D aerofoil and there we got, we drew this with a spring k theta. Okay, this problem, for this we got, because this is the offset E, the divergence speed we got as ud is 2 k theta over s E rho EL alpha. Under root. Okay. Now, what is S? S is area of the wing. What you will get? Area of the wing is? Huh? C into L. Okay, that is chord into length. So, if I substitute here that value and you say that is what my ud, if I consider the full wing, then maybe I, okay, here is here. Comparing these two expressions, then you can find out what should be my k theta, because there is a, if I take this L here, okay, what will happen? This will become L square, right? And you will have Gj over L square, right? And let us write it, k theta becomes Gj over L into okay. That means it is the equivalent torsional spring which you can use in the 2D model, that is essentially Gj over L, because you match it. Is it okay, right? Yeah. So, you will have Gj over L pi over 2 whole square. Now, you see, this is by comparing the divergence speed which we obtained with the 2D model, very simplistic model, and for a uniform wing. Please understand, this is for a uniform wing because Gj is constant along the span. Suppose if Gj is varying, then it's a different issue. Now, there is another way of getting the torsional spring. Okay. If I want to get for a wing, okay, an equivalent k theta, you follow what I am saying? Then I can directly go ahead and use this formula for divergence speed. Now, how do I get that? Okay. That is, the question is, how do I get an equivalent torsional spring for a straight wing, even if Gj is varying? Okay. This is like, I will show the approach. Later we will solve the full problem with the Gj variation. Okay. What is the approximate method? This is another way of approximation. Okay. I think let it be there. Okay. I keep this. What I do is, what is the strain energy of that spring due to a deformation whose amplitude is A, because this is my elastic twist. Okay. And I say that the maximum value when y equal to L, that is this is 1, theta is just A. Suppose if my deformation of this 2D model, this elastic deformation is A, my spring energy will be half K theta A square. Strain energy in the spring U. Now I say, in equivalent fashion, I want to know if that is my deformation, what is my strain energy in the entire wing? That will be 0 to L Gj d theta by dy, Gj free prime whole square dy. Okay. That means if I have this deformation, I am saying the strain energy in torsion is half Gj d theta by dy whole square into dy. If I substitute that expression here and then do the complete integration, because that will become sine, becomes cosine, then you will have pi by 2L term will be there. That part you integrate it, then what you will get is, you will get here half Gj over L pi over 2 whole square A square. Okay. Now if you compare K theta, you will get Gj over L pi over 2 whole square if Gj is constant. Please understand, because I am taking Gj constant in this integration. If I take Gj constant, then I get K theta is this, which is exactly same as matching the divergence speed itself. Okay. Now you know you have a simplistic approach. Quick calculation, you want to know what is the divergence speed of a wing. If you are given a Gj which is, okay, this is a quick calculation only, Gj can be a function of y, then what you do is you are making a highly approximate method. You are going to assume, even though this may not be valid, okay, you are assuming, hey, this is my deformation or the solution, or you say that is what I am going to have as a theta. You simply put that here. Gj is a function of y. You can integrate 0 to L. Okay, you will get some quantity, and A square will cancel out, and you can get an equivalent torsional spring. The moment you get an equivalent torsional spring, you can go and then put it in your divergence expression. And area of the wing, you can take the SS area of the wing. So this is one very quick approximate way of calculating the divergence speed of a wing. Okay. Now let us look at the case where if my wing is not uniform, if my wing is basically non-uniform, then how do I solve the problem? Okay, because this is our because there are two approaches. One is Rayleigh-Ritz, another one you can use Gallartkin method. Okay, so what I am going to do is, now you have for a uniform wing how to get the divergence speed. Now let us take a, and in an approximate way, non-uniform wing also you got here. This is a very crude approximation. Okay. Now let us look at the case if you have a non-uniform wing. How do we get the divergence? Okay. So we will say non-uniform wing and approximate method. Approximate method. The first one is, you can take, this is the Rayleigh-Ritz approach. Okay. What is that Rayleigh-Ritz approach? This is essentially from principle of virtual work we will apply, because you have done one example earlier. What you do is, what is my strain energy? Okay, of the wing during the deformation. Strain energy U becomes half integral 0 to the length Gj d theta over dy whole square dy. This is my strain energy expression. Okay. Now I am going to make approximation, in the sense my theta, which is a function of y, this is the elastic twist which is a function of y, I am going to write it in terms of I running from 1 to n, some ai p I y. Okay. P I y condition is, they must at least satisfy the geometric boundary condition, which is theta equal to 0. Okay. At least they must satisfy that geometric boundary condition. Suppose if it satisfies this also, it is good. That is natural boundary condition also. That is why the choice of the function Py is very, very important. Okay. And you substitute this here, and you write your strain energy expression as U becomes half 0 to L, you will have double summation I running from 1 to n, and then j running from 1 to n, Gj ai aj, I am going to call Pi prime and Pj prime dy, where the prime symbol is basically differentiation with respect to y. Okay. Prime, I am using just the prime symbol, it's easy for me. Now what I can do is take the del u, that is a variation. Principle of virtual work you have to apply. So your del u is you will have your half will go up, you will have Gj, you can have summation I running from 1 to n and summation j running from 1 to n integral 0 to L Gj Pi prime Pj prime Aj dy. I will take this into delta A. Okay, I am writing it like this. Okay. Since you know that these are basically the dy, this Aj is independent of y because Aj is all constant. Only P is a function of y. So you can write this whole thing as summation I running from 1 to n, summation j running from 1 to n. I am calling this as Kij Aj delta Ai, where Kij is my integral 0 to L Gj Pi prime Pj prime dy. Okay. Now you see this is symmetric in the sense I can change I and j. My Kj is same. Okay. Now this is as far as delta u. You have to get the expression for delta w external. Okay. So when we go and write the delta w external, I erase this part now. You have to know what is my delta w integral. I have only a twisting moment. I am not writing the, because I am considering only torsional deformation. I am not considering bending deformation. Okay. Therefore, if you take the cross section, this is our elastic axis and our lift is here, and we said the moment is here, and this is the offset E, and then there is a gravity which is acting. This distance we took it as d. This is nmg. So this is the center of mass, this is the aerodynamic center, this is center of mass. We need to get the moment. So what is the expression for the virtual work? Virtual work, moment into delta theta, because theta is the my deformation. So I give a virtual rotation in theta. Now my moment expression is lift, this moment, and then due to gravity. So lift is q c cl alpha into, I will have, because alpha rigid plus there is an elastic deformation, please understand, into E distance, and then you will have your other momentum which is q c square cm ac. This is the aerodynamic moment minus n mg d. This is the clockwise movement due to gravity load. Now this is my moment expression. I substitute here. Okay. Then I will write my external. If you look at this moment itself, because I am going to now split it, because I don't want to write every time long expression. You see, terms which are independent of theta and the terms which are dependent on theta. Okay. So I am going to write this as m0. The term which is dependent on theta is only this term, qc cl alpha into e theta. The rest of the terms are m0 is q c cl alpha alpha r into e plus q c square cmac minus n mg d. Okay. That means I have split my moment expression like this, because this is a constant moment. Okay. In the sense, this is not a function of theta. It will go to the right hand side of my differential equation. Right. Now I substitute here. I will have integral 0 to L m0 plus q c cl alpha into e theta times delta theta dy. Now what I have to do is I have to go substitute for theta and this expression from my assumed solution. I erase this part. Okay. You will have, this will be integral 0 to L m0 summation I running from 1 to n pi delta ai dy plus integral 0 to L summation I running from 1 to n summation j running from 1 to n, because theta delta theta, that is why two summations q c cl alpha into e, you will have pi pj aj delta ai dy. This is my delta w external. Okay. The delta ai term separately. Okay. And here I have a delta ai. So you apply your principle of virtual work, which is delta u minus delta w is 0. Okay. If you apply this, take out the delta ai. So we will write that expression. Now I erase here. You will have the whole thing as summation I running from 1 to n, you open a bracket, then summation j running from 1 to n, kij aj into delta ai. Okay, that I will keep it as it is. Then you will have minus, I am going to call this term m0 pi dy and q0 I, Q0I, I will define that part later. Then I will have this, because this minus will come and I will have minus. Again I am going to define another term, which is summation j running from 1 to n Qij Aj. Now I will define what is Qi0. Qi0 is nothing but integral m0 pi dy 0 to L, and then Qij is nothing but integral 0 to L Q E C Cl alpha Pi Pj dy. Okay. All right. This is the Qij. That is this expression. Q C Cl alpha E Pi Pj dy. Now, what you immediately go and say is L. My delta AIs are independent, because all the AIs are independent. Therefore, the term within the bracket, that must be 0. Now, if you write that equation, what you will be writing is, I go and erase this part, this side. Okay. You will get a matrix equation which is summation Kij Aj minus, I am going to now take Q outside, because this quantity in capital Qij, this Q is a variable, because Q is dependent on forward speed. So I would like to call this as Q Bij. Okay. Q is, I am keeping it as a separate quantity. So I will have Q summation Bij Aj. Again J running from 1 to n. Here J running from 1 to n equals Qi0 with 1, 2, etc. Okay. Because I have delta Ai, n equations. So this can be put in a matrix form as K A minus Q B A equals Q0. Okay. Now you can put it also in this fashion, K minus Q B into A. But Q naught is a external, that is the other loading which is independent of A, or your deformation. That is what we have said. Now, if you want to get the divergence speed, basically what happens is, as Q increases, okay. Now what happens to this? Because Q can have multiple words. In the sense, this is like, if I want A, what do you do? I take the inverse of this matrix. The inverse will exist only when the determinant is existing. Okay. If the determinant goes to 0, then inverse is infinity. So, from the logic you say, when this determinant goes to 0, then this is like a eigenvalue problem where K minus Q, okay, into A 0. Okay. Now the determinant of this, if it is 0, then this is like an eigenvalue problem. If you set it equal to Q. Now for what values of Q I can have this entire thing goes to 0. Okay. That means K minus QB goes to 0. So you get the eigenvalue problem now. Follow. Now the eigenvalues, the lowest eigenvalue is your divergence. Okay. Now you can have, this is any size you can choose depending on the number of functions you have chosen. I equal to 1 to n. You can choose one function, 2, 3, 4, like that you can have several functions. And then you see how the fundamental eigenvalue, how it converges with increasing number of pi. Okay. Then you will be able to say, okay, this is my divergence field. All right. So this approach is your Rayleigh-Ritz approach. But the interesting part in Rayleigh-Ritz is matrix K is symmetric and the matrix B is also symmetric. Okay. So K is symmetric, B is symmetric. Okay. So this is a symmetric eigenvalue problem you will get. Now we can use this method and get the divergence field for a wing. The same, we got the uniform wing, right? We use the same technique. I'll just, this is just for example. Okay. I erase all these things because it is not necessary now. So evaluation of divergence field is converted into an eigenvalue problem. Suppose we say we take only one mode approximation, only one mode. That means my theta y, I am choosing only A1, that's all, nothing else. Or in other words, I am taking only one mode. Now what is your K11? K11 is integral Gj P1 prime again P1 prime. So you will get P1 prime square dy. What is B11? Which is actually Q11 is, this is a dynamic pressure term we have taken out, B11. This is integral 0 to L, this is 0 to L. I take the Q term outside because Q is independent of the integration. E C CL alpha times Pi Pj. So you will have Pi square, or in other words, I will have P1 square dy. Okay. Now, as per this, I am having only one equation. That means I am taking only one mode. One mode means what I get Q is K by P, that is A11 by B11 is my Q divergence. Okay, so I am going to write my divergent speed as, or QD becomes K11 by B11, which is nothing but integral 0 to L Gj P prime square, P1 prime square dy over integral 0 to L E C Cl alpha P1 square dy. Okay, that means very simple. I got just divergence speed, and I can have, but this is with only one mode approximation. Please understand. If I have a two mode approximation, then I will have a 2 by 2. Then I have to solve for the eigenvalue. Okay, this is just a single mode approximation. Now I will show you this result. If your choice is very good for a same problem which we solved, we will take it P1 as, we will apply this for a uniform wing. Okay, I am using, please understand, for a uniform wing I am solving in this fashion. This is just an example. Okay, if I say my phi1 is sine phi by 2 L y, I am just assuming, because I have to assume some phi1. Now what will happen? Phi1 prime is what? Phi1 prime is phi over 2L cosine phi over 2L y. Okay. Now Q divergence, you will get, substitute there, uniform wing, therefore Gj is constant, E, C, Cl alpha, everything constant. So you will have your Q divergence becomes Gj, and this is P1 prime, so pi over 2L whole square integral 0 to L cosine square pi over 2L y p y. Okay, divided by E C Cl alpha, because it is a uniform wing, everything is taken outside, so 0 to L, this is sine square pi over 2L y. Okay, actually if you integrate this two, they will be same. Okay, you will get Qd becomes whole square Gj over E C Cl alpha, sorry. Now you see this is exact for a uniform wing. What we obtained earlier solution, the divergent dynamic pressure is nothing but Gj by E C Cl alpha pi over 2L whole square. This is the exact solution for a uniform wing. That means my Rayleigh-Ritz technique, even with one mode, please understand, with one mode gives me exact solution, but please understand this mode really, they satisfy both the boundary conditions, because why we got an exact solution is because this is the exact solution of the differential equation, as well as they satisfy the boundary condition. That is why you got the same thing. Suppose, just for the sake of exercise, I am going to choose a function which will satisfy my boundary condition. Okay, that is P0 is 0, P prime L is also 0. Let us take a different function, slightly different function. Okay, so you see this technique gives me exact. I am going to choose slightly different function, which is, I just want to show that here I will write this result, keep it. This is pi over 2L, sorry, pi over 2L whole square Gj over E C Cl alpha. Okay. Now I am choosing a different function, which is 2 y over L minus y over L whole square. Okay. Now you see this is satisfy both boundary, because y equal to 0, sorry, function is 0, that is it satisfies boundary condition. Then dp1 by dy at L, this is first term is 2 over L, second term is 2 y over L square, that is 2 y over L square at L, this is also 0. That means I have chosen a function which exactly my boundary condition, both the boundary conditions, but this is not going to satisfy my equation. So let us see, if I use this function, how my result QD will be. Okay. So my QD is what? Because uniform wing, I am taking same uniform wing only. You will have Gj integral 0 to L P1 prime, this is nothing but 2 over L minus 2 y over L square whole square dy divided by E C Cl alpha 0 to L and the function. You will have P1 square, which is 2 y over L minus y over L whole square dy. Okay. Now if you integrate all these things, okay, I leave it to you for integration. I will write the final answer, which is essentially 5 over 2 Gj over E C Cl alpha into L square. Okay. This is 5 over 2 value. Now let us look at the other result. Other result, which I assumed sine pi over 2L. That is, here I assumed sine pi over 2L into y. For that I got this answer. This answer, if I write it, this is 5 over 2 whole square Gj by E C Cl alpha L square. Okay. If you compare these two results, 5 square over 4, okay, this value is actually 2.4674. Okay, this is 2.5. Okay. Now approximate solution, but of course they satisfy the boundary condition. I am able to get the divergent dynamic pressure, okay, which is very close to the exact solution. Okay. So please understand, this is the approach which is adopted for Rayleigh-Ritz method. Rayleigh-Ritz method, you first choose your function, the approximate function. Make sure they satisfy the boundary conditions. If they satisfy the boundary conditions, then you will find the results are pretty good. You will get a divergence. That's why you choose several functions, keep on, so calculate the same value. But this is with one mode only I considered, because if you really solve an actual wing problem, you need to take more number of modes. You cannot do only with one mode. Okay. But you can use sine in that 2n plus 1 over 2 pi, that value you can choose. Many sine functions you can choose. Okay. And that is the approach you have to do. Because I will give actual wing data, which you have to calculate the divergence speed for that wing. Yes, this is torsional divergence. Yes, bending divergence. There is a bending divergence that will come to swept wing. When you do swept wing, but here it is purely a torsion problem. It is understand. Whereas when you couple bending and torsion problem, that will happen only when you sweep the wing. Okay, that part we will do later, because swept wing, how do you treat the divergence problem? Okay, for a swept wing, because here they will be independent. Bending deformation is, you can split it from torsional, because there is no bending component coming into picture in your torsional equation. The deformation of the bending doesn't come into picture. Only the angle of attack. Angle of attack is purely torsion. Whereas when you go to the swept wing, a bending deformation will come as a change in the angle of attack. Okay. Then these two are bending and torsion are getting coupled. Right now, for this problem, that is why I wrote right in the beginning, it is a straight wing. Okay, not a swept wing. Swept wing problem we will study next. Okay, what we have till now seen is the approach using Rayleigh-Ritz. Now we see how do we apply the Gallartkin method. Okay. So I am going to describe the Gallartkin approach for this same torsional divergence problem. And we know our torsional motion equation, Gj d by dy, Gj d theta by dy plus q e c cl alpha into theta equals minus q e c cl alpha alpha r minus q c square okay c square c plus n m g d. This is my torsion equation. Okay, I am going to show how we use Gallartkin method to solve our divergence problem, because we start Rayleigh-Ritz. Please understand, Rayleigh-Ritz, you start from energy, strain energy, virtual work done by the external source. Whereas in Gallartkin approach, you directly start from the differential equation. Okay. Now what we do is we have to do some non-dimensionalization here, because that makes it a relatively simpler problem, in the sense compact form. So I am going to use a non-dimensional y bar is y over L, where L is the length of the span of the wing. Then you will have d over d y bar of any quantity is nothing but L dy dy of any quantity, because y bar is y over L. And then I am going to use gamma y bar as Gj, which is a function of y by some Gj reference. Okay. Okay, I am going to use a reference quantity. Similarly, I am going to use another data y bar C over C reference, E over E reference, CL alpha over CL alpha some reference. Okay. And then lambda square equals Q L square C reference CL alpha reference E reference over G reference. Okay. Please understand, I am defining these type of quantities. All right. Now I simply go wherever d over dy, I will put it 1 over L d of that function dy bar. Okay, I will replace, and then I will divide by some reference quantities. Okay, this entire equation is converted into, I will write the full expression, then you will know what I have done, and then I will write it in a simpler form. This is for just a little algebra. Okay. So it is going to be a little long. So first term will be 1 over L square d over d y bar of Gj d theta over d y bar. I am dividing by one Gj reference. The entire equation I will divide, plus Q E C C L alpha over Gj reference. Okay. But here I multiply C reference, E reference, CL alpha reference. Again divide by same, C reference, E reference, CL alpha reference equals minus Q C Gj reference into E CL alpha alpha R. This is the first term, Q E C CL alpha. Then second term, Q C square CMAC over Gj reference, then plus NMGD over Gj. Okay. Now what you are basically do is you take this Gj reference inside, then multiply by L square completely. Then what will happen? Gj by Gj reference I define as gamma y. Okay, and then here I have defined lambda square q L square, C reference, CL alpha reference, E reference over Gj reference. So I will take q, there is a L square will come, all these quantities divided by this, I will write it as lambda square. Then the beta y, Ce, Cl alpha, C reference is, so that is this term. Okay, and whatever on the right hand side I will put it as some other loading. Okay, so the equation will become in a compact form. Please understand, I am writing it only for convenience. Gamma d theta dy bar plus beta y lambda square. Beta y means it will be y bar, sorry, lambda square theta k r, where the term k r, which is the right hand side, I am putting it as q c L square. I would say that that entire term is written as a kr. I think I don't have to repeat it again, because I feel it's this entire, I don't have to repeat, please understand. This entire quantity multiplied by L square. Okay, that is the kr. Alright. So for convenience, now you will have this equation as your torsional deformation equation. Okay, so we will use this. I erase all the other things. Okay, so please understand, kr is nothing but square times that right hand side. Now how do we do the Gallartkin? You have to assume theta is a function of y bar, because y is non-dimensionalized. This you are writing it as summation I running from 1 to n ai pi y bar. Very similar to Rayleigh, but only thing is here pi, they must satisfy all the boundary conditions. Okay, so pi must satisfy all BCs. Okay, all boundary conditions. Now what you do is you take this, substitute here, and then when I substitute that function, I will get d over dy bar gamma summation ai pi prime, because please understand I am using prime for differentiation with respect to y bar, plus lambda square beta summation theta is again ai pi, I running from 1 to n, and here now you don't know, this is not going to satisfy my equation. So what I will put it, I take the kr to the left hand side and then say this has an error which is a function of y bar. Okay, kr on the left side. Now I say the Gallartkin technique says that my error is orthogonal to function. So I go back and substitute this condition, because I have to apply this condition, that is integral 0 to 1, because my non-dimensionalized. So I will have epsilon y bar phi, you can take j dy bar is 0 for j running from 1 to n. Okay. So you are going to have n equation, and I am substituting this back. So what you do is you multiply here, put this function in the epsilon y bar, you put this entire thing inside. Okay, and then integrate. What you will get is, maybe I will write that part here. You will have integral 0 to 1 phi j d over dy bar gamma summation I running from 1 to n ai pi prime dy bar plus integral 0 to 1 lambda square beta p j summation I running from 1 to n ai p dy bar, then minus 0 to 1 kr p j dy bar equals 0. You will have j again 1 to n. Okay. This particular thing it as, because you in a matrix form. Okay. The matrix form I am putting it as summation I running from 1 to n k j I a I plus lambda square summation I running from 1 to n b j I a I equals q j r, j running from 1 to n. Okay. Now this entire thing I can put it in a, you know that kji is nothing but this integral 0 1 p j d over dy bar gamma pi prime dy bar, and then b j I, this is integral beta p j p I dy bar, that is this term p j p I dy bar into beta, and then the last term is q j r is k r p j dy bar again 0 to 1. Okay. Now you can put this in completely matrix notation. That will become k a plus lambda square b k is q r. Here again you solve the homogeneous part as a eigenvalue problem. That means set the right hand side 0, because you want to look for a eigenvalue problem, and you will get here the lambda, the lowest eigenvalue is your divergence field. But now I would like to compare this equation with the earlier one. Okay. One interesting thing which you will immediately hit you is my kji, please understand, pj dy bar of pi gamma pi. If I use it in this form, okay, that is pj gamma pi prime, there is a d by dy bar. If I change the index, it's not same. That means my stiffness matrix K is not symmetric. Whereas here it is okay. Here it doesn't matter in the B. Okay. That is why the choice of function, if you had chosen properly, I can do integration by parts here, because this dy, if I transfer it here, okay, then I will have a, this is basically u dv, you will get a uv minus v du. Unless the uv is satisfied at the both the boundaries exactly 0, okay, then only they will be equal. You follow? So you have to be careful. That is why this form, Gallartkin method, of course, if it is a self-adjoint operator, everything, okay, self-adjoint operator, please understand, then both Rayleigh as well as Gallartkin will give same. Because when I integrate by parts, what will happen? I will get, this will go to Pj prime, and Pj prime, Pi prime, I can change, then it is the same thing, okay. But if you leave it as it is, it will be non-symmetric. But then non-symmetric matrices, you cannot guarantee the eigenvalue. See, real symmetric matrix will have real eigenvalues, okay. But if you say real matrix, you can have real eigenvalue, you can have complex eigenvalue. You do not know, you cannot guarantee. That is why when you use Gallartkin approach, you have to proceed in a proper way. Okay, this is the way you will get it, and you may guarantee, because in the swept wing you will see slowly, but you will get a solution. It is not that it's not possible, but these are the fundamental differences between the two approaches. Okay, suppose if the operator is not self-adjoint, that is the reason why we did that self-adjoint and all those things in the translation problem in the beginning of the course, 2 lectures earlier. This is in the form of what kind of final matrix I will land up with, okay. And just out of mathematical, I would say, the approach and the beauty, what will happen if this K is non-symmetric, how the eigenvalues will come. Only thing is you cannot guarantee. See, it doesn't mean that you will not get the real eigenvalue, you will get, but only thing is mathematically you cannot guarantee, okay. So now you see the difference between Rayleigh and the Gallartkin. Both lead to the same kind of form. Only thing is with the plus sign, minus sign, that etc. But that will be taken care of with the formulation itself. Okay.